What's up, gamers? It's me, Elijah, again. Today we're doing the Faraday's Law lab for Physics 2212 at Georgia Tech. Some purpose and background for this lab. Faraday's Law is a law that relates time-varying magnetic field to a curly electric field. And so this path integral around the closed path is not zero, and it provides an EMF that can drive current. And this current in turn produces a magnetic field that exerts a force on the source of the external magnetic field. It's kind of this idea of induced currents. In this lab, the source of that external field is a falling bar magnet, and the induced current is driven by a tube of aluminum foil. The interaction between the falling magnet and the tube of aluminum foil produces a kind of interesting result, which we'll talk about in a couple minutes. So the experiment itself, or at least the physical part of it, uses a tube of aluminum foil, which is with the aluminum foil being at least 1 centimeter thick. We dropped our standard bar magnet that we've been using in this class through the tube and timed how long it took for the magnet to fall through the tube. For my trials, it took an average of about 2.1 seconds for the magnet to fall through the tube because I was using some longer sheets of aluminum foil or longer tubes because that's just what I had available. Some other data points we needed for this include the length of the tube, which is about 18 inches in my case, or 0.4572 meters, the width of the aluminum foil, the inner radius of the tube, and the magnetic dipole moment, which was adjusted from lab 3 to be about 2.5. Here's the first essential part of our computational model, which we are going to kind of walk through piece by piece. This part was all about creating the tube of aluminum foil. And so here in step 1 here, you see the length, width, and inner radius of the aluminum foil. And then as you go down, we get different numerical parameters that we were told not to change. And then there's a function or a for loop to create the tube. The next part of this was all about creating the bar magnet. So we started with the mass of the magnet and the magnetic dipole moment that we showed earlier and calculated in lab 3. For visualizing the bar magnet, we used the functions there with different initial conditions, which really consist of time is equal to 0 and the velocity is equal to 0. And then at the bottom, we wrote a function to calculate the dipole magnetic field, which uses mu and r and returns our value. This was probably the most crucial part of the computational model, was calculating df dt. So here we had the radius of the ring, the distance between the bar and the ring, the speed of the bar magnet, which is that bar dot velocity we found earlier, or we set earlier. And then we kind of use those in a numerator and denominator fashion to plug into our equation and calculate df dt. Here are the final results. On the left, you have a little picture from just part of the computational model. During the model, the red and blue lines fell down to mimic the induced current of the magnet as it fell through the tube. And on the right, we have a velocity versus time graph. And you can see there it takes about 2.85 seconds for the magnet to fall through the tube in our computational model. Some interpretation of this, as I said, the magnet takes, in the computational model, takes about 2.582 seconds to fall through the tube. This was slightly slower than the real-life experiment, and this could be caused potentially by outside magnetic forces pulling the magnet down, such as like something magnetic in the cabinet I was working on pulling the magnet down through the tube. The blue line in the last slide was the counterclockwise induced current, whereas the red line was the clockwise induced current. And if you were to flip the magnet, I believe these currents would just flip. So basically the one that was on the bottom would now be on the top. And the shape of the velocity time graph shows us that the magnetic force is the same throughout the tube. And finally, we had some what if questions, such as what if the resistivity of the conductor were reduced to almost zero? And for this, due to Ohm's law, we know that the induced currents would be larger in magnitude, so the magnet would actually take longer to fall through the tube. Um, and then if holes and slots were cut in the tube, the magnetic force of the tube would decrease, causing the magnet to fall faster. And this is because like the rings on the induced current would be interrupted at every slot.